Welcome to the fifth lecture on inverse trigonometric functions. So, in the previous 4 lectures, we have covered and defined the inverse trigonometric functions. We have also defined identities and relations between them. And in the last lecture, we had started solving some of the problems. So, we will continue to do so. So, this lecture is primarily going to be problem solving for inverse trigonometric functions. So, this is the first problem. So, we have to prove that this left hand side is equal to square root of x square plus 1 over x square plus 2. So, immediately if we see this, it appears a little daunting because there appears to be a composition of trigonometric and inverse trigonometric functions, and there is a nesting of the composition is up to the third level. So, the idea is to actually start with the innermost level. So, that is cot inverse x, and we say that let cot inverse x be equal to theta, and then because the range set of cot inverse is the open interval 0 to pi, it is clear that theta has to belong to the open interval 0 to pi. So, this then becomes sine of theta, and we know that when theta belongs to 0 to pi, from the graph of the sine function, it is clear that sine theta is non-negative. So, because theta belongs to this, we know that sine theta is non-negative, and therefore, we can write sine theta as square root. So, here this is the positive square root of sine square theta, which is equal to the positive square root of 1 minus cos square theta. Now, we need to express this right hand side in terms of x, and therefore, we will use this relation here. So, from this relation, if we take if we apply the cot function on both the sides, what we get is that x equals cot of theta, and therefore, and this then implies that tan theta is 1 over x. And then this can be written as 1 minus 1 over sec square theta, which can then be also written as square root of 1 minus 1 over. We know the identity that sec square theta is 1 plus tan square theta. So, we are going to use that identity over here, which can be further simplified to square root of tan square theta over 1 plus tan square theta. And then in this expression, we plan to use this value of tan theta, which is 1 over x. So, we replace tan theta by 1 over x everywhere in this expression here. So, then what we get is that sine theta becomes equal to the positive square root of 1 over x square over 1 plus 1 over x square, which is equal to square root of 1 over 1 plus x square, and this is the positive square root. And that value we essentially put back in this equation over here. So, what we then get is that we need to evaluate cos of tan inverse sin theta, but sin theta is this value, which is 1 over positive square root of 1 plus x square. So, this is what we are supposed to evaluate. And then again, what we say is that, let us say that this particular value is equal to phi. So, let tan inverse of 1 over square root of 1 plus x square equals phi. Now, since this is the positive square root, this entire value here, this value here is non-negative, and therefore, phi must belong to the interval 0 to pi by 2. So, essentially what we have to find out is cos of phi. Of course, from here it can also be concluded that tan of phi equals 1 over square root of 1 plus x square. Now, this is cos of phi. So, this is what we have to compute now. So, cos of phi. Now, since phi belongs to the interval 0 to pi by 2, from the graph of the cos function, it is clear that cos phi has to be non-negative, and therefore, we can write cos phi as the positive square root of cos square phi, which can then be written as 1 over positive square root of sec square phi, and then again using the identity that sec square phi is equal to 1 plus tan square phi, we get this to be equal to 1 over square root of 1 plus tan square phi. And then of course, in this equation we substitute tan phi with 1 over square root of 1 plus x square, and then that when we do the substitution, we finally get, so we do the substitution tan phi equal to 1 over square root of 1 plus x square, and then we get cos phi equal to 1 over square root. So, this is the positive square root 1 plus square root of 1 plus tan square phi, which is 1 over square root of 1 plus. So, tan square phi is 1 over 1 plus x square, and then this comes out to be equal to 1 plus x square root of 1 plus x square over 2 plus x square, and this is exactly what was asked to prove in the question. So, that finishes the proof of this first problem. So, here is the second problem. So, it states that suppose there is a function f whose domain is 0 to 4 pi and whose range is the closed interval 0 to pi, and the function f is defined as f of theta is equal to cos inverse of cos theta. Then the question asks the number of points theta belonging to the domain of the f function which satisfy the equation f theta equal to 10 minus theta over theta is. So, we have to essentially find how many thetas are there in this domain of the f function such that this value f of f theta is equal to 10 minus theta over 10. So, essentially we need to solve for all the theta belong to the interval 0 to 4 pi such that cos inverse cos theta equals 10 minus theta over 10. So, we need to find out how many solutions to this equation exist in this interval 0 to 4 pi. So, clearly this is because this is a trigonometric we need to first simplify this left hand side over here and then try to equate and see how many such values of theta are there. Now, it is said that theta belongs to 0 to 4 pi. So, clearly when so let us divide this region 0 to 4 pi into 4 regions. So, the first region is 0 to pi, the second region will be pi to 2 pi, then the third region will be 2 pi to 3 pi, and the last, which is the fourth region, will be the closed interval between 3 pi and 4 pi. So, the first case is when theta belongs to 0 to pi. So, when theta belongs to 0 to pi, what is cos inverse of cos theta. Now, when theta belongs to 0 to pi, it is clear that this particular value, well, for any theta, cos inverse of cos theta, let us say it is equal to some angle phi. Now, from the range of the cos inverse function, it is clear that for any theta, phi has to belong to the closed interval 0 to pi. Also, by applying the cos function on both the sides, what we get is cos theta is equal to cos phi. Now, we know that in this interval 0 to pi, just like the graph of the sine function between minus pi by 2 to plus pi by 2, if we look at the graph of the cosine function, so let me quickly draw it over here. So, if we see the graph of cos of x versus x between, let us say, 0 to pi, so let us say this is pi over 2, let us say this is 1 and let us say this is minus 1, and the graph is something like this. And as you can see, the graph, the curve, the function cos x, when limited to the interval 0 to pi, is monotonically decreasing with increasing x. And therefore, if we have two angles, theta belonging to 0 to pi and phi also belonging to the interval 0 to pi. So, both theta and phi belong to the same interval, and cos theta is equal to cos phi. But since the cosine function is monotonically decreasing, the only way this is true is that theta is equal to phi. And therefore, we get that, so this phi is basically equal to theta. So, therefore, we get that for the first case, when theta belongs to 0 to pi, cos inverse of cos theta is equal to phi, which is theta. So, cos inverse of cos theta is theta itself. Now, when theta belongs to the second region, which is between pi and 2 pi, it is clear that for this case, cos inverse of cos theta cannot be equal to theta, because this value cos inverse of cos theta has to belong to the range set of cos inverse, which is 0 to pi, and this theta is belonging to the interval pi to 2 pi. So, therefore, to be precise, what we can do is that we can define this second region to be pi to 2 pi, but it will be open from this left side. So, the value of pi does not belong to the second region, and this is because we had defined the first region to be the closed interval. So, pi belongs to the first region. So, now it is clear that for the second case, when theta belongs to pi to 2 pi, it is clear that cos inverse of cos theta will not be equal to theta. So, then how do we find the value of cos inverse of cos theta? Now, as usual, let us say that this is equal to some x, then it is clear that this x has to belong to 0 to pi, which is the range set of the cos inverse function, and then if we apply the cosine function on both the sides here, we end up getting cos theta is equal to cos x. We realize one thing over here, which is that since the cos function is a periodic trigonometric function, cos of 2 pi minus theta is also equal to cos theta. And the reason why we took 2 pi minus theta was because if theta belongs to pi to 2 pi, then that implies that 2 pi minus theta would belong to the interval 0 to pi. So, therefore, what we see is that if we essentially what we see is that if theta belongs to pi to 2 pi, then 2 pi minus theta belongs to 0 to pi, and this interval is actually a subset of the range set of the cos inverse function. So, therefore, what we have here is that we have an angle 2 pi minus theta. So, let us say this is phi. So, we have cos of phi is equal to this value cos theta, and we know that this phi belongs to the range set. We know that this phi, which is 2 pi minus theta, belongs to the range set of cos inverse. So, we know that phi belongs to the range set of the cos inverse function, and therefore, since cos phi is equal to cos theta, it is immediately clear that phi must be equal to cos inverse of cos theta. Hence, in this case where theta belongs to pi to 2 pi, it is clear that cos inverse of cos theta will be equal to phi, where phi is 2 pi minus theta. So, therefore, in this case, in the second case, cos inverse of cos theta is equal to 2 pi minus theta. So, cos inverse cos theta is 2 pi minus theta. Similarly, for the third case where theta belongs to 2 pi to 3 pi, again in this case also cos inverse cos theta will not be equal to theta, and in fact we can show that when theta belongs to 2 pi to 3 pi, theta minus 2 pi will belong to the interval 0 to pi, and further that cos of theta minus 2 pi is equal to, so this is equal to cos of theta. So, again we have a similar situation here where cos of this angle is the same as cos theta, and we know that this angle theta minus 2 pi belongs to the range set, because this particular interval here is a subset of the range set of the cos inverse function, and therefore, we know that this angle belongs to the range set of cos inverse, and from therefore, it follows that theta minus 2 pi should be equal to cos inverse of cos theta, and therefore, for when theta belongs to this interval 2 pi to 3 pi, cos inverse of cos theta will actually be theta minus 2 pi. And the same thing is true for the last scenario where theta belongs to 3 pi to 4 pi. So, in this case we see that 4 pi minus theta. So, if theta belongs to 3 pi to 4 pi, 4 pi minus theta belongs to the interval 0 to pi, which is again a subset of the range set of cos inverse. Further, cos of 4 pi minus theta is equal to cos theta, and this again is because of the periodicity of the cosine function. So, cos 4 pi minus theta is cos theta, and 4 pi minus theta, this particular angle belongs to the, so this one belongs to the range set of cos inverse, and therefore, again from here it follows that 4 pi minus theta is equal to cos inverse of cos theta. Hence, when theta belongs to this fourth interval, cos inverse cos theta is actually equal to 4 pi minus theta. So, if we now we can now summarize the these 4 different cases in this slide here. So, this slide tells us the value taken by this function cos inverse cos theta for all the different ranges of theta. So, this precisely defines the cos inverse cos theta function. So, in this graph we have plotted both the curves for the function cos inverse cos theta as well as the function tan minus theta over 10. So, on the horizontal axis we have theta, on the vertical axis we plot the values taken by these two functions. So, in black we have plotted the graph of the function cos inverse cos theta. In blue we have plotted the graph of the function tan minus theta over 10. And we see that since we were asked to find out all those values of theta for which these two functions take the same value, or for which cos inverse cos theta equals tan minus theta over 10. So, that is what was being asked, and it is very clear from the graph that both these curves they intersect at first of all over here, and then the second time they intersect here, and then the third time they intersect here. So, there are basically three distinct values of theta for which cos inverse cos theta is equal to tan minus theta over 10. So, the final answer to this question will be the number of points theta belonging to 0 to 4 pi satisfying the equation tan minus theta over 10 equal to cos inverse cos theta is 3. So, there are only 3 distinct points. In the next problem we are asked to solve the following inverse trigonometric equation. So, we have to solve and find all those values of x which satisfy this equation here. So, the same thing can be written as tan inverse 2x is equal to pi over 4 minus tan inverse of 3x, but we know that tan of pi by 4 is 1, or rather tan inverse of 1 is pi by 4. So, we replace pi by 4 by tan inverse of 1, and therefore, the right hand side is equal to this expression here. And then we have to use the formula for tan inverse x minus tan inverse y, or rather we can actually write it as tan inverse 1 plus tan inverse of minus 3x. So, we need to use the tan inverse x plus tan inverse y type of formula, which we have already seen in one of our previous lectures. So, here is the expression. So, for this case what we have now is that we have x equal to 1 and we have y equal to minus 3x, and we see that the product of x and y is minus 3x for this case. So, one more thing that has to be observed for this problem is that the value of the tan inverse function, so this particular value and also this value. So, both these values add up to pi by 4. So, now if x is negative, then we know that if x is negative, this value will also be negative, and therefore, and also this value. So, therefore, if x is negative, then this entire thing will be negative. But since in this problem we have been asked to find out those values of x for which this is positive, it clearly can be basically concluded that only those x will satisfy this equation for which x is greater than 0. So, that is something that we can immediately see from this equation here. So, therefore, in the subsequent discussion we will only restrict our discussion to positive values of x. So, again coming back to the tan inverse x plus tan inverse y formula. Now, we know that since x is positive for our problem here, So, what that means is that y is negative because y is minus 3x, and therefore, x times y. So, we have x times y is less than 0, and therefore, out of these three cases, our case will basically be this particular case, because for us x y is less than 0 and of course 0 is less than 1. So, in our case for our problem x y is less than 1, and therefore, we have to use this particular formula with x equal to 1 and y equal to minus 3x. And when we do that, we get this right hand side to be equal to tan inverse of 1 minus 3x over 1 plus 3x. And then we have, so finally what we get is that tan inverse of 2x is equal to tan inverse of 1 minus 3x over 1 plus 3x. Now, clearly, because we know that if tan inverse A is equal to tan inverse B, if this is true, then it must be true that A is equal to B. Then it must be true that A is equal to B. And therefore, I mean that this can be seen by just applying the tan function on both the sides of this equation. So, we apply tan on both the sides, we get A equal to B. And therefore, using this fact in this particular equation, it follows that this is true if and only if 2x is equal to 1 minus 3x over 1 plus 3x. And then if we work it out a little bit, of course, then we have a little bit of algebraic manipulation which gives us this, and then we have 6x square plus 5x minus 1 equal to 0, and the left hand side can be factored as 6x minus 1 into x plus 1 equals 0. So, there are two solutions now. So, x is either 1 over 6 or it is minus 1, but we already know that x must be greater than 0, and therefore, this is not, minus 1 is not a valid solution. So, the only possible solution is x equal to 1 over 6. So, this is the final answer. So, here is another very interesting problem, and I think it is one of the JEE problems. So, it says that if x, y and z are in arithmetic progression, and tan inverse x, tan inverse y and tan inverse z are also in arithmetic progression, then which of the following is true? Now, since x, y and z are in arithmetic progression, we have y is equal to x plus z over 2, or in other words y minus x is equal to z minus y. Now, tan inverse x, tan inverse y and tan inverse z are also in arithmetic progression, and therefore, that fact can also be written as tan inverse y minus tan inverse x is equal to tan inverse z minus tan inverse y. Now, let us denote this angle by theta. Let us say it is non-negative. Now, let us make the following observation. So, let us say this is minus pi by 2 and this is pi by 2. Then for this case, it should be true that tan inverse z is greater than tan inverse y, and the least is tan inverse x. So, and this are, so these are equal, these angles are equal in measure. And because these two angles are equal in measure, and all of these tan inverse x, tan inverse y and tan inverse z have to lie in the interval minus pi by 2 to plus pi by 2, it follows that the magnitude of this angle, so let us say if theta is positive, then so it follows that this is theta and this is also theta, and therefore, if we add both these thetas, we get 2 theta, which is this value. So, it is clear that this 2 theta should be less than the length of this entire interval, which is pi, and therefore, it is clear that theta should be less than pi by 2, or because the tan inverse function is actually an open interval. So, that is why we have strict less than here. So, essentially we have theta greater than or equal to 0 and less than pi by 2. So, now let us apply the tan function on both sides of this equality. Now, we know that this angle theta is between 0 and pi by 2, and therefore, tan of theta can be written as tan of tan inverse y minus tan inverse y minus tan inverse x. So, here we are going to use the tan of a minus b formula. So, let us say this is a and this is b. So, this will be equal to tan a minus tan b over 1 plus tan a tan b. So, tan a is y minus tan b is x over 1 plus x y. Now, because this theta is between 0 and pi by 2, it follows that this value of tan theta, because when theta is between 0 and pi by 2, the graph of the tan function takes non-negative values. So, this has to be greater than or equal to 0. So, from here it clearly follows that we have tan theta equal to this value, and theta of course belongs to this interval, which is actually a subset of the range set of the tan inverse function, and hence it follows from here that theta must be equal to tan inverse of y minus x over 1 plus x y. And similarly, the same thing can be done for this right hand side. So, the right hand side here, which is tan inverse z minus tan inverse y, will come out to be equal to tan inverse of z minus y over 1 plus z y. And because they are equal, we finally have this equality, and this basically implies that now we just need to apply the tan function on both the sides of this equality, and therefore, what we get is that this value here is equal to this value here, which we write as y minus x by 1 plus x y equal to z minus y over 1 plus z y, and then further simplification gives us that y minus x into 1 plus z y is z minus y into 1 plus x y, and then y plus z into y square minus x y z is z plus x y z minus y minus x y square. Now, we know that because x, y and z are in arithmetic progression, y minus x is equal to z minus y, and therefore, these 4 terms cancel out, and then what we get is 2 x y z. So, we take this term on this side is equal to, and then we bring this term on the left hand side, y square into x plus z, but then x plus z is equal to 2y, and that is because x, y and z are in arithmetic progression. So, this becomes 2y cube, and that can be written as 2 into y square minus xz equals 0. So, in the interest of time, without considering the second case, even for the second case where we consider this value to be negative, and if we just follow a similar derivation, we are also going to arrive at this condition, and therefore, it follows that this is a necessary and sufficient condition. So, this is a necessary and sufficient condition if both x, y, z and tan inverse x, tan inverse y and tan inverse z both of them have to be in arithmetic progression. So, this is a necessary and sufficient condition for that. Now, from here there are only two possibilities. So, either y is 0 or y square is xz. Now, if y is 0, so if y is 0, so if y is equal to 0, then we have x plus z equals 2y equal to 0, and we also had that tan inverse x, tan inverse y and tan inverse z are in arithmetic progression. So, well, this will be, so this we are taking the case y equal to 0 here, but this is 0. So, and x plus z is 0. So, for this case, since z is equal to minus x, so this actually implies that z is minus x. So, then this third tan inverse of z becomes equal to tan inverse of minus x, which is minus of tan inverse of x. So, of course, this is one possibility that y is equal to 0, and therefore, we have x 0 and minus x. So, this is z is minus x. This is in arithmetic progression, and also tan inverse x 0 and minus tan inverse x. So, these three are also in arithmetic progression. So, this is one possibility, and the other possibility is that y square is equal to xz. So, this is the other possibility, but this actually implies that x, y and z are in geometric progression, and at the same time we have x plus z equal to 2y, which basically means that so this means that they are in arithmetic progression. So, because x, y and z are both in arithmetic as well as geometric progression, the only possible way is that x is equal to y equal to z. So, we only have two possibilities. So, the possibility number 1 is this possibility that y is 0 and z is equal to minus of x, and the second possibility is that possibility number 2 is that x, y and z are all equal. So, these are the only two possibilities, and if we go back to the multiple choice question that was asked, so since y equal to 0 is not mentioned here, the only possibility that is correct is this first scenario. So, all of the other ones are not correct. So, we take up another interesting problem here. So, in this problem it is said that the value of x is in between 0 and 1, and then we are asked to find the value of this very lengthy expression here. So, as always, we always go to the innermost expressions, because this is a nested, because here we have a trigonometric composition of a trigonometric and an inverse trigonometric function. So, we start off with defining cot inverse x to be equal to theta. Now, because x is between 0 and 1, it follows that theta must belong to the open interval 0 to. So, because it is 0 and 1, it should actually belong to the interval from pi by 4 to pi over 2. So, this follows from the graph of the cot inverse function. And then we just replace, of course, from here it also follows that x is equal to cot theta, and then we replace this cot inverse x by theta everywhere in this equation here. So, then whatever is inside this big equation becomes, so this root of 1 plus x square becomes root of 1 plus cot square theta, which is root of 1 plus 1 over tan square theta, which is equal to root of 1 plus tan square theta over tan square theta, which is can be further simplified because this numerator here becomes sec square theta, and that sec square theta is 1 over cos square theta. So, this will finally simplify to 1 over sine of theta. It should be also noted that for theta in this range, sine theta is strictly positive. So, the expression, so what we try to do is that we try to move this root of 1 plus x square inside this other square root, and then what we get is square root of the square root will not be there anymore because it will be 1 plus x square into x cos theta plus sin theta whole square minus 1 plus x square. So, this is what we get. Then we can try to move this 1 plus x square inside this expression. So, that will be square root of 1 plus x square times x cos theta plus sin theta whole square minus 1 plus x square. But we know that this square root of 1 plus x square is actually 1 over sin theta. So, we use this fact now. So, this is essentially 1 over sin theta, and that is what we use here. So, we get this to be equal to square root of x into cos theta over sin theta plus 1. So, this when divided, so we divide both these by sin theta. So, this becomes 1 and this becomes x cot theta. So, eventually we have root of x into cot theta plus 1 the whole square minus 1 plus x square. But we know that cot theta is in fact equal to x. So, we replace this by x, and then we finally get square root of x square plus 1 the whole square minus 1 plus x square. And this, if we simplify further, we get this to be equal to square root of x into square root of 1 plus x square. So, this finishes the computation of this expression, which we have found to be equal to x into square root of 1 plus x square. So, let us take the next problem. In this problem, we have to find the number of positive solutions which satisfy this following inverse trigonometric equation. So, by positive solutions, we mean the values of the variable x which are positive. So, x greater than 0, which satisfy this inverse trigonometric equation. So, as we can also see in this equation, on the left hand side we have an inverse, we have the sum of the tan inverse of two different values. So, this immediately reminds us of the tan inverse A plus tan inverse B type formula. So, just for you to recollect, we had in one of the previous lectures proved this particular identity that tan inverse x plus tan inverse y can be written as the tan inverse of x plus y over 1 minus x y if the product x y is less than 1, and if the product x y is greater than 1, then if both x and y are positive, then we just need to add plus pi. If x y is greater than 1, but both x and y are negative, then we need to add minus pi. for this current problem at hand, what we see is that since we are only interested in finding the number of positive solutions, so x greater than 0. So, whenever x is greater than 0, it is clear that 1 by 2x plus 1 is also greater than 0, and so is 1 by 4x plus 1. So, both of these arguments of the tan inverse function are positive, and therefore, obviously this particular case is ruled out. So, the only two cases which can now apply are either this case or this case. But we also see that if we see this value, if x is greater than 0, then 2x plus 1 is of course greater than 1, and therefore, 1 by 2x plus 1 has to be strictly less than 1 and of course positive. So, this is so 1 by 2x plus 1, which is the argument of the first tan inverse here, is between 0 and 1, and a similar thing can be said about the second argument here, which is 1 by 4x plus 1. So, we see that both 1 by 2x plus 1 and 1 by 4x plus 1 lie between 0 and 1, and therefore, from this it follows that the product 1 by 2x plus 1 times 1 by 4x plus 1 has to be also less than 1, because both of them are less than 1, and therefore, if we come back to our formula, we see that the out of these two cases, the case which applies is x y less than 1, which is that the product of the two arguments of tan inverse x plus tan inverse y. So, the arguments are x and y. So, the products x and y, if it is less than 1, then this first case is applicable, which is true here, because the product we have already shown the product to be less than 1. So, therefore, we have tan inverse of 1 by 2x plus 1 plus tan inverse of 1 by 4 x plus 1 to be equal to. So, we will use this first formula here, tan inverse of this plus this over 1 minus the product of these two values and which can be simplified to this expression here. In the problem, it is said that we need to find a positive, we need to find positive solutions, which means that we need to find positive values of x, such that this expression is equal to tan inverse of 2 by x square. So, we want this to be equal to tan inverse of 2 by x square. So, from this equality over here, so this and this are equal, and therefore, it follows that this argument here should be equal to 2 by x square. That is 6x plus 2 over 2x plus 1 times 4x plus 1 minus 1 equals 2 over x square. And if we simplify this expression algebraically, what we end up getting is that x must satisfy this polynomial equation, and this can be further factored out as x into 3x square minus 7x minus 6 equals 0. So, this can be further factored out also. So, we can write 3x square minus 7x minus 6 as 3x plus 2 times x minus 3. So, from here it is clear that there are exactly 3 values of x which satisfy this equation, and the values are x equals 0 from here, x equals minus 2 by 3 because of this factor, and x equals 3 from this last factor. But if we go back to the problem was asking us to find the number of positive solutions which satisfy this equation, and from here it is clear that this is 0, this is minus 2 by 3. So, the only positive solution is x equal to 3, and hence the number of positive solutions satisfying this equation is equal to 1. So, the number of positive solutions satisfying this equation is 1. So, there is only one solution, which is x equal to 3. So, that finishes this fifth lecture, and we will continue to do some more problems in the next lecture, which is going to be our last lecture on inverse trigonometric functions, and thereafter we plan to start a new topic where we discuss the properties of triangles, where I think a lot of this material that we have covered for the trigonometric functions and the inverse trigonometric functions is going to be extremely useful. Thank you.